Hey everybody, welcome to today's lecture for analysis of algorithms. Today's lecture, like lecture 11, is on stable marriage, which is why it's called stable marriage part 2. And just like lecture 11, it's based on section 4.3. Okay, so the first thing I just want to be absolutely clear on is that the book has a lot of information which is not in the lecture. And I can test you on anything that's in the book. So watching this lecture is not enough. The lecture is meant to supplement the book, right? It's meant to make it sort of easier to understand the book. Okay, so in lecture 11, we talked about how we can test whether a set of marriages is stable. So we talked about the concept of stable marriage, we talked about why it's useful, and then we did the stability check algorithm, right? But that gave us an algorithm that allowed us to check whether a set of marriages is stable. But it didn't get us to the point where we could actually create a set of stable marriages. Okay, so what we're going to do this week is we're going to talk about how we can take the set of preferences that we have and turn it into a set of marriages. Okay, now the algorithm we're going to talk about in class is called the Gale-Shapley algorithm. Okay, and it's quite an interesting algorithm because it's kind of familiar. So how it works is that you've got this set of boys and girls and they've all got their preference arrays. You remember those? Now, how the Gale-Shapley algorithm works is that boys will propose to girls and girls will either accept or reject those boys, right? Now, boys, because they want to end up with the best possible girl they can, will propose in order of their preference. So the first person they'll propose to is the girl they like the most, and then after that, the girl they like the second most, and so on and so forth. And they'll stop when there's some girl who, will accept the proposal and stay with them. Okay, so the behavior of boys is pretty straightforward. They just propose to girls in order of preference. The behavior of girls is, I guess, also kind of familiar. A girl, if she receives a proposal, will basically accept the best proposal if she accepts lots of proposals, right? But how the mechanics of this works is that because all of this happens sequentially, a girl will receive a proposal, right? If at the time she has not yet received any proposals, she'll accept that proposal. Okay? So nobody's ever proposed to her. So now someone proposes and she's like, hell yeah, right? Then, if subsequently she receives another proposal, meaning someone else proposes to her, it's not the first time she's been proposed to. What she'll do is she'll accept the best proposal. Okay, so if boy 1 proposes to her and boy 3 proposes to her, she will initially get engaged to boy 1. And then when boy 3 proposes, she'll say, well, do I like boy 3 more than I like boy 1? If not, I'll stick with boy 1. And if yes, then I'll switch to boy 3. Okay, so basically she'll leave her fiance if she likes the boy that's just proposed to her more than she likes her fiance. Okay, now in order for this algorithm to run computationally, we'll need to keep track of the preference arrays, right? Because we said boys propose in order of preference, but I mean, we can only know the order of preference if we have a preference array for each boy. We said that a girl will decide whether to accept the proposal based on whether she likes the boy more than the person she's currently with, which we can only do if we have a preference array. Okay. We also need a marriage array. For one thing, that'll store our answer. That'll tell us who people are married to at the end. But while the algorithm's executing, it'll also keep track of who each person is currently paired with, right? Who they're engaged to. Okay. Then we said boys propose in order of preference. So that means we need to keep track of who the boys have already proposed to so that the next person they propose to will be the first girl that they hadn't previously proposed to. So basically for a boy, if he proposed to his favorite girl and she rejected him, there's no point proposing to that girl again, right? She rejected him. You got to move on to propose to the next one. So you got to keep track of which girls have already rejected you so that you can propose to the next one. Okay, so that's the point of the proposal array. Okay, so let's do an example. Let's run through the algorithm. Let's see what it looks like. So the algorithm as we had it on this sheet was just boys propose to girls in order of preference, and girls will either accept or reject based on who they like more. We're going to make it slightly more concrete, not that much more, but we're going to turn it into almost pseudocode. We're going to say, while there is some unmatched boy B, let G be the first girl that B has not proposed to. Okay? So, this is basically saying that you want to propose in order of preference. So the first girl that you haven't proposed to. If that girl is unattached, so we're going to now propose to her, right? So if she's unattached, then B and G must now be matched. Okay, so they'll be engaged. Otherwise, meaning she is attached. If G prefers B to her fiancé, then unmatch her from her fiancé, so she breaks it off with her current fiancé, and match B and G because she likes B more than she liked her fiancé B prime. Okay? Otherwise, just leave B unpaired. Basically, otherwise he got rejected. Okay? So we're going to go through this as an example. So the first thing we do is we say, let's pick the unmatched boy 0. Right? Okay, sorry, I'm using man and woman and boy and girl interchangeably, so just bear with me on that one. So let's say we start off with man 0. Okay? Now man 0 will now propose to his favorite girl, right? The first girl that he hasn't previously proposed to. The first girl in his preference array that he hasn't proposed to is girl 0 or woman 0, right? Question then is, so here's our matches. Is woman 0 currently married? Well, no, she's not, because, nobody's married. Is she currently engaged? No one's engaged, right? Nothing's happened in this algorithm yet. So that means woman 0, because she hasn't currently got a fiancé, will accept the proposal. Okay? So that means we've now got a match. Man 0 is matched with woman 0. Okay? And we move on. We then say, okay, well, there's still some unmatched boy, in this case man 1. And man 1's favorite girl is girl 2. So he's going to propose to girl 2. Okay. Girl 2 is also unmatched. So since she's unmatched, she's going to say, okay, I accept the proposal. And that means that man 1 is now engaged to woman 2. Okay. Then man 2 is unmatched. So he's going to propose to woman 2. But woman 2 now is not unmatched. She's with man 1. Okay? So woman 2 must now decide, does she like man 2 or man 1 more? Okay? And if we look at this, her favorite man is man 1. So that means she likes man 1 more, and that's who she's currently engaged to. Okay? So that means she's going to reject man 2. So man 2, he's out of luck. So he's still unmatched, which means he's now going to propose to woman 3. Okay? And woman 3 is unattached. Okay? So that means she's going to accept the proposal. Man 2 is therefore going to be married to woman 3. Okay? Now it says, while there is some unmatched boy. Well, we look at these men 0, 1, and 2 are matched. So man 3 is the one that's unmatched. So he's going to propose to woman 0. Okay? Now, woman 0 is not free. Right? She is currently with man 0. So the question now is, does she prefer man 0, who she's currently with, or man 3, who just proposed to her? And if we look, her favorite man is man 3. So she prefers man 3. So what she's going to do is she's going to leave man 0 and instead become engaged to man 3. Right? So she's gonna run away, basically. Okay. So then it says, while there is some unmatched boy B, so man 0 is unmatched. Okay. So he now is going to propose to the next woman in his preference array. Okay. In this case, he's going to propose to woman 2. Okay. Now the question is woman 2 unattached? No, woman 2 is currently married to man 1. And if we look at woman 2, she's happy with man 1. Man 1 is her favorite. So she's not going to leave man 1 for man 0, who's the least favorite. Right? So she stays where she is. So man 0 is out of luck again. So man 0 now proposes to woman 1. Okay, and woman 1 is unattached. So she's going to agree to get engaged to man 0. Okay. And so at this point now, everybody is married, and this set of marriages is stable. Okay, meaning there's no one in this set of marriages who will run away from their current partner. Okay. So yeah, that's basically how the Gale-Shapley algorithm works. Now, what's really cool about it is you can it's intuitively reasonable, right? You can kind of see that this is sort of similar to how the real world works. Again, we talked about last week why this problem is kind of artificial. There's an equal number of men and women, and there's no gay marriage, and every man and woman have to get married, right? So it's not the same as the real world, but there's some sort of closeness. Okay, so now I said that when we finish here, there's a set of marriages and everyone's married and those marriages are stable. But is that true? Does this always work? Okay, so the first question is, does the algorithm terminate? Okay, so we've got some while loop, and it's possible that this while loop will never end, in which case the algorithm will not terminate, right? Now, every time this thing runs, it's possible that B stays unpaired. It's also possible that some other B prime becomes unmatched. So it's not true that every time the while loop runs, some unmatched boy becomes matched, right? It's possible that a boy stays unmatched, or that some other person actually becomes unmatched who was previously matched. So there's nothing to say that as we go through this while loop, boys are getting matched, and eventually there won't be any unmatched boys. Okay? Basically, engagements are created and destroyed inside this loop. So it's possible that the loop will just never finish. Or is it possible? Well, the thing is, boys just run down their preference lists, right? So the boy will propose to girl 1, to his favorite girl, then his second favorite girl, then his third favorite girl, all the way down. So eventually the boy will run out of people to propose to. Right? So each boy can propose at most n times, right? He can propose to as many girls as there are. He can't propose any more because he never proposes to a girl twice. He just goes down his preference array. Okay? And there are n boys. So there's at most n squared proposals. Every boy proposes n times and there's n boys. Okay? So the algorithm will terminate just because boys will run out of people to propose to. Right? Well, sort of. The next question is, okay, fine. The boys do run out of proposals. The algorithm terminates. But is everyone married at that point? So let's think about this. If a boy at the end of the execution is unmatched, right? He has proposed to everybody, right? Because he went down his preference array. That means everyone in the entire list rejected him. Okay, first of all, that sucks to be that guy. But if we think about it, a girl will only reject him if she's already with someone better, right? So a girl won't reject a proposal if she's got no other options. Okay, so that means when he proposed to every girl, they were attached, right? If any girl wasn't attached, she would have accepted him. So every girl was attached at some point. Okay, but the interesting thing about the way the algorithm works is that if a girl is attached, she never becomes unattached, right? So a girl can break off an engagement, but only to enter another engagement. Okay, so a girl never becomes free. If at any point a girl is in an engagement, she will always be in an engagement, right? So that means every girl was in an engagement, because that's why they rejected him. But there's n girls and n boys. There's an equal number of girls and boys. So if every girl is engaged, they have to be engaged to somebody, right? So it's not possible that there's some boy who's unengaged when all the girls are engaged. Okay? So that means at the end, everyone must be married. Okay, I'm not sure that made sense, but if you were struggling with it, please try and go through it again, or look at the explanation in the book, which is a sort of alternate. And if still it doesn't make any sense, then of course ask me on WhatsApp. So we've said the algorithm terminates. We've said that everyone is married when it terminates. But is the set of marriages always stable? So does Gale-Shapley produce stable marriages? Meaning, can we be certain that none of the marriages it produced will end in divorce? Okay, well, let's look at that. So let's look at a particular marriage in the set. Boy X is married to girl Y, right? It's just some random marriage in the set. Okay, we're not going to put any restrictions on that. It's literally just any marriage that we found in the end. Okay. Now, boy X is married to girl Y, but let's say there's some girl Z that he likes more, right? So remember, with stable marriages, it doesn't mean the boy ended up with his favorite girl. It just means he ended up with a girl that, or sort of, he ended up in a marriage that is 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 not going to end in divorce. Okay, but remember, we said for a marriage to end in divorce, it's not sufficient for the boy to like another girl more than his wife. It also means that that girl has to like him more than her husband, right? Remember, the boy is not going to run away from his wife unless he has a better option. Okay, so boy X is currently married to girl Y. He's not going to leave girl Y unless there's some girl Z that he can leave her for, right? So let's let girl Z be a girl that boy X likes more. Now, boy X didn't end up with girl Z when he was, in the marriage set, because boy X ended up with girl Y. But he proposes in order of preference, right? So since he liked girl Z more than girl Y, he would have proposed to girl Z, and then she must have rejected him because he didn't end up with girl Z. He ended up with girl Y, who he liked less. Okay? So she, girl Z, rejected him. And let's say she then ended up with boy A. Okay? Now, the thing is, she must like boy A more than she likes boy X, right? Because otherwise she wouldn't have rejected boy X. She'd have rejected boy A. Okay? So the point is, she rejected boy X for a reason, and the reason is she liked boy A more. Now that means that boy X can't run away with girl Z, right? Because girl Z doesn't like him enough to leave her husband. Okay? And notice we didn't put any restrictions on who boy X and girl Z were. So for any choice of boy X, we found that there's no way that any girl Z that he likes more than his wife will also like him, right? Because like here when I said let BXGY be a marriage in the set, I didn't specify that it's a particular marriage. And when I said let GZ be a girl that BX likes more, I didn't say which one. It can be anyone, right? So that means it's true for all girl Zs. Okay, so that means if boy X likes a girl Z more than his wife, she automatically doesn't like him more than her husband, and so the marriage is stable. Okay, so for all boys, there is no girl that would leave her husband for him, who he would also leave his wife for. I know that's a bit convoluted. Yeah, but it kind of makes sense. Okay, so we know the marriages are stable. But there's one super interesting fact about this algorithm. And that fact is that the Gale-Shapley algorithm, which remember actually looks a lot like the real world, results in the best possible set of stable marriages for boys. This is if boys do the proposing. If girls propose, it results in the best possible set of marriages for girls. Okay. Now, a point of clarification here. That doesn't mean that boys end up with their favorite girl, because a marriage to their favorite girl may not be stable, right? Their favorite girl may just leave them at the first opportunity. But from all possible sets of stable marriages, so if we can say there's lots of ways to end up with stable marriages, the Gale-Shapley algorithm ends up in the best possible set of marriages for boys. And here's how powerful this statement is. It doesn't mean that it's the best for boys on average. It doesn't mean that it's the best for most boys. It's actually the best for every single boy, meaning there's no boy that could possibly end up with a better girl than the one that he ended up with under the Gale-Shapley algorithm. Okay, so that kind of indicates that our current system for doing this in the real world is really heavily biased towards boys, which is kind of cool if you're a boy. Okay, so can we prove that? So we want to prove that the male-oriented Gale Shapley, meaning the ones where the males propose, results in the best possible set of stable marriages for boys, which is the male optimal set. Okay, so this is theorem 4.5 in the book, and the proof is written down quite well there. I'll be a bit informal here, just to make it a bit easier to understand, but it's not a good thing to do when you're doing a proof, is to be super informal. So we're going to use a proof by contradiction. As a side note, let's talk about how proof by contradiction works. Okay, so let's say we have a chain of statements that are implications, basically. So A implies B implies C implies D implies E implies F implies G. Okay, what does that mean when you get right down to it? What it means is that if A is true, and I'm using green to signify true, then B must be true, right? Because A implies B, and C must be true, and D must be true, and E must be true, and F must be true, and G must be true. Okay, so if we have this chain of implications, if A is true, then G is true. Okay, it just keeps the truth, basically. It's similar to what we were talking about with induction. The truth is almost, it goes viral, and it just goes down this list, right? But let's say that I don't know anything about whether statements A through F are true. Okay, if I know that G is false, then A must be false, because if A is true, then G is true. And I know that G is false, so A must be false. Does that make sense? So if G is false, that forces A to be false, because if A was true, G would have to be true. Okay, so how we do a proof by contradiction is we start with a statement A that we don't know whether it's true or false, but we're trying to prove that it's false. Okay, that statement is called our assumption. And then we just construct a chain. So we say, well, look, A implies some other statement, B implies some other statement, C implies some other, and we just keep going until we get to some statement that we know is false. And then because it's false, that means A is false. Okay, so that's how proof by contradiction works. Now, in our particular case, we're trying to prove that Gale Shapley is male optimal. So the statement that we're going to try to prove is false is that Gale Shapley is not male optimal. Right? So we're going to assume that Gale Shapley is not male optimal just because we want to prove that statement to be false. Okay, so first some definitions. We're going to call the set of marriages produced by Gale Shapley M_GS or M subscript GS. Okay, I'm just going to call it MGS as I speak because I don't want to pronounce the underscore each time. Now, the set of marriages produced by Gale Shapley is called MGS, and our assumption is that it's not male optimal. Okay, and if it's not male optimal, there must be some set of marriages M subscript X, which I'm going to call MX, in which some males are better off than in MGS. Okay, so there must be at least one man in MX, or there must be a set of marriages such that at least one man is better off than in MGS. If that isn't the case, then MGS is male optimal, right? Because there's no other set of marriages in which a man is better off. Okay? So one thing just as a note is that MX is not produced by Gale Shapley, right? MGS is produced by Gale Shapley. MX is just some arbitrary set of marriages. We can think of it as being created by magic. Right? So in MX, there's no such thing as proposals and rejection and that sort of thing. It's just some magic arbitrary set of marriages. MGS, on the other hand, is produced by Gale Shapley, so we know some things about how it's produced, right? Now, when we were producing MGS, the boys proposed in order of preference, right? Now, there's some boys in MX who are better off than they are in MGS, okay? I guess the best way to explain this is think of these as parallel universes. They've got the same men and women in them, these two parallel universes. But in MGS, in the parallel universe with MGS, the boys have ended up, or people have ended up in one set of marriages, and in the other parallel universe, they've married other people. Okay, and these two separate sets of marriages are MGS and MX. Now, what we're saying is that in the universe with MX, some boys are better off than in MGS. Okay? And since boys proposed, in MGS, the boys proposed in order of preference, they would have proposed to the people that they married in MX but got rejected. Right? Because if they ended up with someone worse, it's because they got rejected by the by the person they prefer. And since Gale-Shapley is a sequential algorithm, there must be a boy who was rejected first, right? I don't mean this is the first time a boy was rejected globally. I mean, it's the first time a boy was rejected by the person they got married to in MX. Okay? I know this sort of parallel universe construct is a little bit hard to follow, but I think it's the best analogy I have for how this works. So let boy I be the first boy who was rejected by their partner in MX. Okay? And his partner in MX is girl J. Okay, so he ended up with girl J in MX. But when MGS was happening, in the universe MGS, girl J actually rejected him. Now, the only reason she rejected him is because she's with someone better. Okay, let's call him boy K. Okay, so that means girl J must like boy K more than boy I. Otherwise, she wouldn't have rejected boy I, right? She would have rejected boy K. But she didn't. She rejected boy I, which means she likes boy K more. Now, boy K has proposed to girl J already, right? Because they're already together. That's why she rejected boy I. Okay? Now, we said that boy I was the first boy rejected by his partner in MX, right? That was let BI be the first such boy. Okay, so boy I is the first boy rejected by his partner in MX. So that means boy K has not been rejected by his partner in MX yet at this point in the execution, right? But he's already with girl J. So that means he's already with girl J, but he hasn't proposed to his partner in MX. Which means that he likes girl J more than his partner in MX, because remember, he proposes in order of preference. And he's already proposed to girl J, but he hasn't yet proposed to his partner in MX. Okay. Now here's the interesting thing. We know that girl J likes boy K more than she likes boy I, who's her partner in MX. Right? So in this universe MX, girl J likes boy K more than her husband. Right? But we also know that boy K likes girl J more than his wife in this MX universe. So that means boy K and girl J will run off together because they both like each other more than they like their partners. And that means that MX is unstable. Okay? But our statement over here said let MX be... Okay, I clearly messed up in the slides. But our assumption should have said let MX be a set of stable marriages in which some males are better off than in MGS. Okay, so I'm going to fix that on the slide, but I'm not going to fix that on the video because that's too much effort. Pretend this let MX set be a stable set of marriages. But the point is, it said let MX be a set of stable marriages in which some males are better off than MX. But now MX is not stable. So that's a contradiction. Okay? And the only thing we assumed was that MGS was not male optimal, right? So our assumption, that statement A, according to that chain of statements, was that Gale-Shapley, the male-oriented version of Gale-Shapley, doesn't produce a male optimal set of marriages. But we found a contradiction, so that means it does. Right? So that means there's no other stable marriage set in which any boy has a better partner than in MGS, which is quite a big statement, right? It's not that this on average the boys end up better off. It's that every single boy ends up in the best possible situation they can end up in when we do things the way they're done in the real world. So yeah, we got it good. And here's the slightly more depressing result. So the male optimal version of Gale-Shapley, we said it produces the best possible set of stable marriages for boys. The really interesting thing is it produces the worst possible set of stable marriages for girls, meaning that in the sort of universe of possibilities, if we take all the different parallel universes, using the Gale-Shapley algorithm, the one that we fundamentally use in real life, means that every girl ends up with the worst possible boy they could end up with without the marriage ending in divorce. So That's pretty bad. And what's even more depressing is that this is not because of the Gale Shapley algorithm. This is a consequence of it producing the best possible set of marriages for boys. Okay? So, what's really interesting is the best set of marriages for boys is automatically the worst possible set of marriages for girls. Okay? And as a side note, like I always bring up my wife when I talk about this stuff, because the poor woman, she's like, she makes more money than me. She's a second dan black belt in karate, so if there's like a noise in the middle of the night, I'm sending her to investigate it. She's way prettier than me, so like fundamentally the only thing I got going for me is Gale Shapley, and I'm really glad I do. So this idea that the best set of marriages for boys is automatically the worst possible set of marriages for girls is a proof that I've asked in every exam going back a really long time. I said last 5 years here, but it's probably even more than that. And I've never taught it. So look it up and try and understand it, because it's one of those things that's almost always in exams. But yeah, and I mean, I think it's very interesting because I've seen debate, where people say it's so much harder for boys because boys have to propose, and it's so much easier for girls because they don't have to do that. And plus, girls get the advantage of being able to accept or reject, so they're in a better position. But it's not true, and the reason it's not true, or some intuition of why it's not true, is because the girls can only accept or reject based on the boys that propose to them, whereas the boys get to propose to their globally favorite girls. Right? A girl doesn't get to make a decision about her favorite boy if that boy doesn't propose to her. Okay, so yeah, it's a very interesting structure, and remember that this comes from the hospital intern problem. So it's not that we were trying to model marriages, and like I say, it's a very imperfect model for real world marriages anyway. But I think it's a quite interesting result that we get there. And I guess it's implying that if you're a girl, you should overturn the status quo and ask out the guys that you like. And on that note, thank you all for listening. There will be a quiz about this week.